Hello everyone, you're watching NeriChem. The Nobel Prize for Chemistry was announced just 2 days ago. I think we should probably have a look at it. So, metal organic frameworks is the reason why the 3 men who have received the prize have done so. What is a metal organic framework and what can we learn about them? So, a metal organic framework is just basically you have a metal cluster which has organic ligands, and it forms a porous structure. These are solids. So what does this mean? Why is that interesting? So you have a car which needs fuel and you're using hydrogen for fuel. How do you transport the hydrogen in the car so that it can use the fuel? Well, one way of doing that would just be to have a gas canister. So if I draw a car, so if I have a canister of hydrogen gas which isn't pressurized, I might have a car which looks like this. And this is hydrogen gas, molecular. So the problem with this is that if my parking space looks like this, it is relatively trivial to see that the car will not fit inside of the parking space. Whereas if the gas is pressurized, in that case, my car will look a lot more reasonable. It might look like this. Fantastic. And now it will fit inside of the parking space. But I have just introduced an issue, which is that molecular hydrogen gas is tiny. It is really, 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 really small. That means it wants to leak through any substance. In fact, if you have a balloon, so imagine this is my balloon, and it's got hydrogen gas, you will notice that sometime later, your balloon will look like this. Why? Because the hydrogen gas can actually travel through the rubber. It's that small. So what's the problem? Well, basically, this only gets worse the more you compress the gas. So if I have a small canister, my hydrogen gas will want to escape even more. So why is a metal organic framework useful? Well, if you create a solid which acts analogous to a sponge, as in it can absorb hydrogen gas, then your hydrogen gas isn't going to be pressurized. I could put my hydrogen gas in here, and then I can simply put that little block of my porous substance on top of the car.
All this being said,
Hydrogen storage, politically correct, not that interesting, but dative bonds, now that is what I'm talking about. So HKUST1 is the name of the molecule I'm going to be talking about. HKU stands for Hong Kong University. They put their own name in the name of the molecule. Anyway, I'm not sure I would do that. Maybe I would. I don't know. I've never invented a molecule, you see. So I'm going to draw the structure of HKUST.
a few seconds later,
Any suitable substance which could fit inside of this material could, for example, fit in this gap here, in this gap here, this one here, and this one here. And actually in HKUST1, there's 2 pore sizes. One is bigger than the other, and then the other one is in the center. Now, where are the dative bonds? That's a fantastic question. So I'll tell you where the dative bonds are. So I've just drawn this. This isn't a skeletal formula. So these black lines which I've drawn here do not necessarily represent carbon-carbon bonds. That would mean this molecule would be really weird and would break apart. It wouldn't work. It's just a generic structure I've drawn. Actually, these black lines represent a more complex structure which involves the following molecule. So this is the organic ligand. But I spoke about metal clusters in metal organic frameworks. So we've covered the organic part of the MOF, but what about the metal part? So in HKUST1, these are copper, metal ions, although I think that you can have different metals, but I'm just going to focus on copper for the moment. So here we have copper, which is bonded to another copper. And you can see here in the carboxylic acid, this area here is where we are going to have an interaction between the organic molecule and the metal. And it's going to come from these carboxylate groups. Although I haven't drawn them as carboxylate, they're drawn as carboxylic acids. But I can rectify that in the diagram I'm showing below. So imagine I have an oxygen here from the carboxylic acid, and this goes up, and this wiggly line just means the structure continues, and the rest of the structure is this here, and the same below, and the same in front, and the same behind the two copper atoms. Excuse me, this line should not exist. Here we go. So you can see that we have 4 carboxylate groups which are binding to 2 copper metal ions. Now, the copper ions, which I'll label in orange, these are copper 2+. So these have a double positive charge, both of them. They each have a double positive charge. Now, the reason why I'm using this Nobel Prize to teach dative bonds is because the metal organic framework wouldn't work without dative bonds, because this is a coordination complex. Coordination complex. And coordination complex don't work unless you have dative bonds. These are the dative bonds, the ones I'm highlighting here. Perfect. So this was a pedagogical opportunity which I have exploited, used. Now, what is a dative bond? A dative bond. A dative bond is a 2-electron, 2-center bond where the 2 electrons come from the same atom. So there you go, that's the definition of a dative bond. Really important to remember and to commit to memory. Fantastic. So let's analyze using the Lewis formality these dative bonds. So X is going to denote electrons which come from the oxygen, and circles are going to denote electrons which come from the carbon. So because this is a double bond, it would be XO, XO. So oxygen is in group 16, so it has 6 valence electrons, so there have to be 6 X's around the oxygens. The oxygen with a negative charge will have this electron here, which means therefore it has a -1 charge. So what happens is, another way of drawing this would be like this, where we have oxygen here and oxygen here, and instead you might have 1, 2, 3, 4, 1, 2, 3, 4. So in total, between the 2 atoms, you have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7. So that's 6 plus 7 equals 13. Okay, so we have 13 electrons. So divided by 2 would be 6.5. Okay, so we have 1, 2, 3, 4, 5. Now we need to draw 6 here, and then you see how an X is kind of like a less than and a greater than symbol. If I divide that by 2, I can draw half an electron on each side, which I'll draw in black. Perfect. So it's almost as if I have half an electron on each oxygen, and the reality is that the electron density is equally and symmetrically spread amongst these two oxygen atoms. But because I'm drawing a Lewis formality, the best way of doing that is to draw either a dotted line like this, or to just simply draw half an electron on each oxygen atom. Although we know that that's not a physical reality, you can't actually divide electrons by 2. And then because these are 2 electron bonds, then if I were to draw 2 copper atoms, one here and one here, then that would mean that I would have these 2 electrons and these 2 electrons bonding to the copper atoms, which have a bond amongst each other. And these are, of course, dative bonds. So just for reference, we saw that the copper was in the 2+ state, and the carboxylate anion, which is CO2 minus, has a single negative charge. And you can see that the overall charge in this case is neutral, because this is -1, this is -1, this is -1, and this is -1, and this is +2, and this is +2. So 2 + 2 - 1 times 4 equals 0. So overall neutral. Although, just fun fact, this is, as far as coordination is concerned, this is unsaturated, meaning you could fit water ligands here and here, which would make this a hydration complex, but we have drawn this in the unhydrated form. That's as much as I will say about dative bonds and metal-organic frameworks. I hope this has been useful, and I'll see you in the next one. Goodbye.